Let's now take a look at the general definition of a concave function. This one here. And so we have a and b in the interval I. Let's put x1 instead of a and x2 instead of b. 1 minus lambda can be written as lambda 1. Lambda can be written as lambda 2. Then the same definition, I can say that the function f of x is concave on I if for all x1 and x2 in I, and for all lambda 1 greater than equal to 0 and lambda 2 greater than equal to 0. Again, you have lambda 1 plus lambda 2 equal to 1. You are going to get this. So earlier what we had was this. Let's say if I get to the earlier definition, I know that the function, let me write that definition here. F is concave in the interval I if for all a b belonging to I and all lambda belonging to this, we have f of 1 minus lambda a plus lambda b. This has to be greater than equal to 1 minus lambda f of a plus lambda f of b. Now in this case, instead of 1 minus lambda, I put lambda 1. Here this is lambda 2. A is now x1, b is now x2. So obviously 1 minus lambda plus lambda, okay, if I go for 1 minus lambda plus lambda, this is going to be equal to 1. That just means I can write in this case that lambda 1 plus lambda 2 equal to 1. Also, lambda is greater than equal to 0. That means lambda 2 is greater than equal to 0. 1 minus lambda is also greater than equal to 0. That just means, so if I write 1 minus lambda greater than equal to 0, that means lambda is less than equal to 1. So what we now do is, that just means lambda 1 is greater than equal to 0. So here lambda 1 is greater than equal to 0. Lambda 2 is greater than equal to 0. So given this, I can now write this definition. I can rewrite this definition in this manner, that f of x is concave on I if for all a b belonging to I, so I just write if for all x1 and x2 in I and for all lambda 1 greater than equal to 0 and lambda 2 greater than equal to 0 with lambda 1 plus lambda 2 equal to 1. We have this f of 1 minus lambda a plus lambda b. So I can just write f of lambda 1 x1 plus lambda 2 x2 greater than equal to 1 minus lambda f of a. So I just write 1 minus lambda. Instead of that, I write lambda 1 f of a. So it's f of x1 plus lambda f of b. So I write lambda 2 f of x2. When we generalize this inequality, what I have written here, when I generalize this inequality, what I get is called a Jensen's inequality. When I generalize this inequality, we get Jensen's inequality. And now let's take up Jensen's inequality. So for that, as I said, we are going to generalize this. That means we now don't have just x1 and x2, we have x1, x2 till xn. So that's how I'm generalizing this inequality, and that's when I get Jensen's inequality. So here I write a function f is concave in the interval I if and only if for all x1, x2 till xn in I, and for all lambda 1 greater than equal to 0, lambda 2 greater than equal to 0, lambda n greater than equal to 0, with, please keep this in mind, with lambda 1 plus lambda 2 plus dot 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 plus lambda n equal to 1, we have this f of lambda 1 x1 plus lambda 2 x2 plus goes on plus lambda n xn. F of this is greater than equal to lambda 1 f of x1 plus lambda 2 f of x2 plus lambda n f of xn. So this is the Jensen's inequality, and if I want to think of the function being convex, we just have to reverse the signs. So for that, I'll just write it is convex when we have this. So that's Jensen's inequality. Now we take up a very important question which relates to production smoothing. So let's say we are considering a manufacturing firm, and that firm is producing a single commodity. The point to note here is that the cost of manufacturing, or the cost of maintaining, let's say, the cost of maintaining an output level Y per year for a fraction lambda of a year is lambda C of Y. And I know here that C prime Y is greater than 0, C double prime Y is greater than equal to 0 for all Y greater than equal to 0. And we know that as far as the firm's output is concerned, the firm's output I'll just explain what I mean by the cost of maintaining an output level Y per year for a fraction lambda of a year is this. So the firm's output in this case is, it can fluctuate. over the year. The firm's output can fluctuate over the year. What we have to show here in this question is that we have to show that given the total output Y, given the total output Y, that the firm produces over the whole year the firm's total cost per year is minimized by choosing a constant flow of output. So we have to show that we are given that the total output Y is produced by the firm over the whole year, given that the firm's total cost per year is minimized when the firm chooses a constant flow of output. So just to understand this, let's get back to our question. Let's go over it again. We know that the cost of maintaining an output level Y per year for a fraction lambda of a year is lambda multiplied by C of Y. C prime Y I know is greater than 0. C double prime Y is greater than equal to 0 for all Y greater than equal to 0. That just means that the function is convex. The firm's output, I know it can fluctuate over the year. We have to show that given the fact that we have a total output Y which the firm produces over the whole year, we have to show that the firm's total cost per year is minimized by choosing a constant flow of output. So for that, if we are concerned about this constant flow of output, so let's just suppose first that, so let me write, suppose the firm chooses different output levels, not the constant flow but different output levels, Y1, Y2 till Yn per year for fractions of the year, and we know about those fractions, lambda 1, lambda 2 till lambda n respectively. What does that mean? Let's say we divide the year into 3 parts. So 1 by 3, 1 by 3, 1 by 3. First, firm chooses the output level 60 per year. Fraction of the year, for 1 by 3 fraction of the year, the output would be 20. Let's take up that. It's just as an aside that I'm considering this. It's 60 per year. So Y1 is 60. But if we choose this Y1 for a fraction 1 by 3 of the year, it is going to be just 20. It is going to be 20. In the next 3 months, let's say, not in the next 3 months, in the next 4 months. So the first 4 months, the output is 20. The next 4 months, let's say the output is, for that, as a firm, I choose 18 units of output per year. But in those 4 months, we are going to then have 6. So it will be 6 plus, again, now for the last 4 months, I choose output 30. per year. That means the last 4 months, those would correspond to the production of 10. So in that sense, I'm saying that the firm chooses different output levels per year. So here the output level per year is 30. Sorry, here it is 60. Here it is 18 and here it is 30. So the firm chooses different output levels y1, y2 till yn per year for fractions of the year lambda 1, lambda 2 till lambda n respectively. Keep that in mind that these fractions are greater than or equal to 0 and lambda 1 plus lambda 2 plus dot 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 plus lambda n, all of these add up to 1. Clearly here we have 1 by 3 plus 1 by 3 plus 1 by 3, so that adds to 1. Now what we do is, given all this, if I want to know about the total output, so total output y will be equal to summation lambda I yi, I varying from 1 till n. Basically, there in that case what I had written there was this. So total output would be, so it's 60 into 1 by 3 plus 18 into 1 by 3 plus 30 into 1 by 3. 60 is y1, 18 is y2, 30 is y3. 1 by 3, 1 by 3, 1 by 3, these are lambda 1, lambda 2 and lambda 3. So given this, I can say that the total output is going to be this. It will be produced at, this will be produced at total cost. Now about the total cost, I know everything here. I know that the cost of maintaining an output level y per year for a fraction lambda of a year, same concept, that is lambda c of y. So the total output, the total cost in that 1 year is going to be equal to summation lambda I c yi, I varying from 1 till n. I know that my function c, that the c function is convex. So now what I do is I apply the Jensen's inequality. So what I now do is applying the Jensen's inequality to the convex function c, we have this. So if I get back to the Jensen's inequality, it is this. For the convex function, it is this less than this greater than equal to this. So that means I have, it is lambda 1 f of x1 plus lambda 2 f of x2 till lambda n f of xn. So that means I can just write now in this case summation lambda I c of yi, I varying from 1 till n. So this is greater than equal to f of lambda 1 x1 plus lambda 2 x2 dot 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 plus lambda n xn. So that means I can now write greater than equal to c of, it was lambda 1 x1, so it is going to be lambda 1 y1, lambda 1 y2, lambda till lambda n yn. So this is going to be equal to summation lambda I yi, I varying from 1 till n. And this I know is equal to C of y. That I know already. And that just means that the total cost is this, that is greater than equal to this. So what does the right hand side indicate? That is actually, so what is this? This is the cost of maintaining the constant output level y over the whole year. And we see that this is, and this I know is the minimum cost, because what we see is that this is my total cost, and total cost is greater than equal to this. It is greater than equal to this. It just can't be less than this. So that means the minimum cost is the cost of maintaining the constant output level y over the whole year, and that is exactly what we had to show, and we have proved this with the help of Jensen's inequality to the convex function C.